Okay. I'm just going to start with a very brief presentation. It's just the 5 slides, including this title slide, just to explain what the motivation was and what some of the issues are. I take personally, I take great pleasure from what I've done, and I'm proud of it. But I'm not going to make any claims that this is an earth-shattering project. It is to develop a Forth for uh, single board computers using RISC-V. Started more or less about a year ago, because at the time it looked as though we were going to get a flood of single board RISC-V computers onto the market. There was a big fuss in January last year about Beagle 5, which was going to be the first low-cost, mass-produced RISC-V SBC. Unfortunately, although prototypes were made for that and they were sent out to be tested, that project has been cancelled, though there is hope that we're going to see other RISC-V SBCs in the year ahead. There is actually one on the market now, the Neja board, which I do have. It's not really, it's not particularly low cost. It's about $100 US dollars, I think. And it's not been huge numbers made, but it does work. It's got a 1 gigahertz single core processor on it, and it's what I do actually now do most of my development on. But you can also use QEMU, and originally I started off by using the Spike emulator. So why did I do it? Well, for fun mostly for my own fun, and then hopefully to be able to give some pleasure to other people who were using these RISC-V SBCs. I mean, my immediate motivation was that I thought that with these coming onto the market, and when you look at the ecology around the Raspberry Pi, it would be good to have something which allowed people getting these RISC-V SBCs to get some easy access to the hardware and do stuff with hardware without necessarily having to deal with all the boilerplate that comes with other languages. And Forth seemed like a good option. Partly also because, I mean, I admit I'm a child of the 80s in computer terms, and when I first started using basic uh, computers, microcomputers in 1981-82, Forth was always held up then as the sort of faster alternative to basic. So it's always held a fascination for me, although I hadn't actually really done anything with it. So I thought it would be a good thing to go and develop my own. I also had this naive belief that nobody else would actually have made a Forth for RISC-V processors, when actually, you can see that there are quite a lot of different varieties out there. So how's the project evolved? Well, I originally started Christmas time last year with the view that it was only going to last a few weeks, partly because the book that I had, which you could get online, about threaded interpretive languages, says it only takes a few weeks to develop a Forth for Z80 processor. So I thought that would be pretty simple. It's obviously been now going for a year. I started off with the idea that I'd write a threaded interpretive language, which would be similar to Forth, but I wouldn't really necessarily stick to the standard. The longer I've gone on, it became more Forth-like, and now actually my view is what I'm really trying to do is match something which meets the Forth standard. And I do actually now meet most of the 2012 core standard. So there's been quite a lot of progress on that. It's all, I mean, one of the interesting things about the standard versus the hardware I'm using is the standard's obviously written on the basis that cells are 32 bits wide, while the hardware is 64 bits wide. So, I mean, I'm really using stuff which is everything is 64 bits wide. And as I said, it runs on the Neja single board computer, and it will also run on QEMU. There are some pretty serious limitations with it at the moment. It doesn't have any floating point support. It doesn't really have any graphical or even sort of sophisticated text output. It's just basically it's very it is very 1981 style lines of text output. There aren't really any other users. I mean, maybe that's because I could say that's because there isn't really any other hardware out there. When I say there's no hardware support, what I mean is, although my original motivation was to write something which would allow people to hack the hardware, I haven't really written any sort of specific hardware support code. I mean, I'm really concentrated on the core language itself. And that's because there isn't really a big community out there at this moment in time. So it's seemed more opportune to get on with building up the support for the language, the core language, rather than looking at the hardware. And in terms of what will come next, I mean, I could actually adding the floating points support and curses and curses type support isn't that particularly difficult. It's really a question of finding the time. There is OpenBSD which runs on QEMU, and it would be quite good to port to that. I don't think that's going to be particularly that would be that challenging a thing, just making sure that the library commands all match. And it would be good at some point to get this packaged for Linux distributions, which are for RISC-V. And it would obviously be great to get more users, contributors to the project. So that's the sort of the background to it. And if I can work out how to do this, I will now actually show you it running. Okay, just bear with me a second. Got to share another screen. So hopefully you can still see a blank terminal screen. Nobody's saying anything, so I'm taking that as a yes.
Yes.
Okay, right. So if I just run it, I mean, it's a pretty crude interface here. But I mean, it does the basic things that you would need. There is an issue about some of these the words. They aren't defined in the way that you would expect. Just there might be in the full text form. That's to do with, I mean, that's a sort of technical debt which I still haven't dealt with in terms of how the assembly works for these. I mean, basically I have an issue with assembly macros and equal signs. So GTEQ is actually greater than or equal to, and you can actually write that out as that in the code, but when it comes up as a listed word, it comes up on that form. And I think the thing to do is just show you the tests that so you can sort of see this gives you an idea of the words that are supported. It's nothing particularly exciting. And that's it, basically. So that's a quick run through of it, and this is just some of the code, just so you can see what it looks like. and it is all written in RISC-V assembly. In terms of performance, just one additional sort of thought. And some things, I mean, I've essentially measured it, not in a particularly sophisticated way, but measured some of the timing performance against GForth, and some things it does. I mean, it's about 10% faster than GForth. Other things, I've basically noticed that the my create seems to be probably a bit slow. So I think I need to work further on optimization of that, because when I've run a proper matrix multiplication benchmark code, my code's about 10% slower than GForth. So, and I think just from some crude profiling that I've done, I think that's to do with the way the create code works. And I've got some thoughts about how to deal with that. But I mean, in general, it runs at a reasonable speed. But it's not, I make no claims that it's particularly super fast just because it's written in assembly. So that's my sort of run through of it. And if anybody has any questions, I'd be more than happy to answer them.
Yeah, right. Thank you very much. And are there any questions?
Yes, Christian has a question.
Go ahead.
My question is there any RISC feature that makes it better for Forth? You wrote something, you wrote Forth with it. You must know all the features that help you.
Well, I haven't written a Forth for any other language, any other sort of processor. So in one sense, I don't have a comparison to draw there. I don't. I mean, the idea behind RISC-V is to have an open and clear instruction set at the assembly level, rather than, if you look at the x86 family, they've essentially been, I believe, if you average out over the last 40 years, one new instruction has been added per day, essentially, over the last 40 years in that family of processors, and that is not proposed here. At some point in the future, RISC-V will quite likely to have a vector instruction set, which could be quite useful. It's not in any of the cores I'm using, so I don't get any particular advantage out of that. I mean, it was written. I decided to go down this way, writing one for RISC-V on the basis that I thought that we were going to get quite a lot of low-cost RISC-V single board computers on the market this year, and that hasn't happened.
So RISC-V was chosen mostly because it's a free instruction set.
Yes, I mean, I had essentially just completed a PhD, and I'd used RISC-V in that, so I had a bit of familiarity with the instruction set, and I thought it was, there's no shortage of, at least this was my view, there is no shortage of language support and coding ideas and similar things for ARM and for Raspberry Pi users. So I thought, well, there might be some new users of RISC-V single board computers. Let's produce something which will be useful and helpful to them.
I heard you mention vector instruction. Could you explain what it is?
Well, the idea, so that is the idea that you essentially apply a single instruction across a large number of memory locations or registers, all in parallel, all at once, so that you can essentially, you can get a lot faster arithmetic. So it's quite useful for sort of heavy computational arithmetic tasks, possibly graphical processing tasks, those sorts of things. I mean, essentially, I mean, I'm not speaking from experience here, but rather from my understanding. But if you think of a a sort of a supercomputer, a very parallel supercomputer. It is set up to do this, the same calculation in parallel millions of times, and very quickly. Having a vector instruction set allows you to replicate a little bit of that in a single processor.
Thank you for taking the time to explain.
So that's no problem.
You satisfy my curiosity for today.
Okay, thank you.
Great. So Dimitri, you raise your hand. And the mic.
Yes, I think I'm on. Okay. Yeah, I might not ask the question completely correctly, but I've always wondered this because I've been into RISC-V for a few years, and one of the things I always thought of is you have, I think, 31 registers normally that are available. And what would happen with a language like C is it kind of uses them like a stack. It's not a real stack, but it's almost as if it's a stack when it's evaluating the expressions. But I thought, well, that's a very difficult thing though to do in a Forth implementation. So I wondered how registers or RiscV would be used when implementing a Forth on RiscV. So my question then is, how many of the registers did you use?
Okay, I'm just going to quickly consult my book here just to make sure I can get the count numbers right. So just bear with me a second.
Could be used exact as a PDP.
Sorry.
You need at least 6 registers.
Well, I mean, so in the way that the registers are structured, I mean, obviously in theory you could use any register for whatever you liked, but this is the standard way that they are used is you have 7 temporary registers, so they can be used for anything you like, and I just tend to use those for sort of general computational stuff. You have 8 registers which are used for function arguments, and certainly if you're passing anything to the C library, you need to sort of set those up. But they are inside your own code. You can essentially use those in any way you see fit. And then there are a further 12 saved registers, which the values of which are meant to be preserved from one function call to another. Now, what I actually do with that in Forth is that I do cheat a little bit with those, because I know then that if I put store values in those registers, when I call into the C library, they won't be, the values there will not be changed. So they are quite useful for using as stack registers inside Forth, because you know that they will be preserved from call to call. So I don't use, I'm only using 3 of them, but I do use them as things which will be immutable as you sort of pass back and forth to the C library. So that's how I use that. You can also, I mean, in some 1 or 2 places, I push a lot of registers to the stack, so that you can then use more registers as well, in the same way that would be familiar to anybody who's written functions in assembly before, so that you can just sort of stick everything on the stack, do what you like with the registers, and then just pull them all off the stack at the before you return. So there's 1 or 2 places I do that, but in general, temporary registers just used for routine calculations. The function registers used occasionally for routine calculations, and sometimes to call into the C library. Save registers generally don't touch, except that those ones which I use to ensure that I've got immutable stack pointers, which will be preserved as I call in and out of the C library.
Okay, that's really interesting. So you've actually used the RISC-V ABI when designing this. Okay, that is really interesting, and how you've used the save registers for the stack pointers, but you were following the ABI. Okay, thank you. That answers my question.
Okay. Right.